Okay, this is the second coastal processes lecture, and we finished off the first one looking at the difference between the east and west coast and how tectonics controls the shape of the coastline. So now we're going to move on to from the main five processes that are controlling coastal appearances and look a little bit more at detail on the beaches and then some more on tectonic features as well. So there's many different types of beaches, but one of the most basic ways to break it down is on based on the steepness of the beach face. So how steep the sand is. And the reason for breaking it down this way is because that changes over time as a result of the different types of waves that are interacting with the beach. So one of the really important points to put in your notes here is that the wave type dictates the shape of the beach, but at the same time, the shapes of the beach dictate the wave types. So it's another example in geomorphology of equilibrium, like feedback, two different processes sort of working against each other. And we'll see how things kind of change over time. So the two basic types of beaches are reflective and dissipative. So this is a picture of a reflective beach, and the main characteristic of a reflective beach is a relatively steep beach face. So this area from the from the water line to where the beach goes from a slope back to a flat is what we call the beach face. And then you have what's called the back shore, which is the flatter area back here. So a reflective beach is pretty steep. A dissipative beach is less steep. So here you can see there's far less sand. There's actually some bedrock sticking out. In general, big waves over a long period of time will create a dissipative beach. And that's because the power of the waves removes the sand. This becomes a high energy environment, and all that sand gets kind of transported offshore and it sits out just underneath the wave action. Whereas a reflective beach, what happens is usually this is a result of smaller wave action that sort of piles up sand onto the beach. Now, there are exceptions to that, and another important factor is how much sand is being delivered to the coast, which we talked about in the last lecture. But in general, reflective beaches are mostly small waves. Dissipative beaches generally form from large waves. But again, this can change over time. You have a long period of large waves hitting the California coast. A lot of that sand moves off, and you got a dissipative beach. But then you might have the following month just small waves, and the small waves push and pile the sand back up onto the beach. Okay. So the beach shape is constantly changing. It's constantly adjusting to changes in the waves, changes in tides as they move up and down. This is just one example. This is from a jetty at Bolsa Chica, where you can use rocks to actually identify a marker to see how beaches are changing over time. So this is not a large change, but you see how this is more gentle shape to the beach here. And then at this time, you have a pretty steep sort of almost cliff formed in the sand right there. And then this part also is just slightly steeper. But the big change is right here where some sand has been removed over time. And so this is just a few days apart. Okay, about almost 2 weeks apart. This is a little closer view where you can see that the wave action has been eroding and it's created a little cliff in the sand itself. Obviously, this is not going to stay very long because the sand is not consolidated bedrock. It'll just collapse over time. But the high tide is hitting that section there. So this diagram, I would probably stop the lecture at some point and retrace this in your notes just to make sure you've got it. This is showing the different characteristics of the beach, and so this is showing kind of all the different characteristics, and that doesn't mean that it's present on every beach. But the more important ones are what we call the beach berm, and the beach berm is the break and slope. It's the transition from the kind of flat backshore area, which is the area of sand that's above high tide, where high tide typically is not reaching, and the beach face or the foreshore area where the tide is reaching up and down every day. So here is the beach face, and then you have the backshore, and this little inflection point, that change in slope right there, is the berm. Then sometimes you'll have a low tide terrace, kind of a flatter area off there. You can get little troughs forming. You can get bars, also sandbars forming. This diagram shows one. Sometimes you can get multiple sandbars formed. That's where sand is getting deposited by the wave action. So the waves are eroding it off the beach and then moving it out, and then it gets deposited wherever the energy is lower. So once the water gets deep enough that the waves are not disturbing that area, that's where the sand gets dropped. These characteristics up here, these classifications, are less important. So it's really the different sort of beach morphology. And then later on in the lecture, I'm going to go in a little more into this, the sea cliff, and the bedrock wave cut platform that is present underneath the sand. So you might want to take a look back at this figure a few times and get a little more familiar with it, especially in light of the field trip. So here's some examples from the Huntington Beach area that's covered on the field trip. But so here you have the back shore. This is sort of like the floodplain of the beach. It's equivalent to a floodplain on a river. So the water most of the time doesn't make it back here, but during extreme high tides and big waves, you can get water coming over the top of the berm and reaching the back shore. So then the berm is that inflection point, and then you've got this beach face. So here would be the current water line, and generally the berm is corresponding to just above or right at high tide. So the high tide typically comes up almost to the beach berm, right? So the beach face is dictating, or is kind of representing, the area between high and low tide. Now, in some beaches, you oftentimes see two berms. And so what this is an older berm from a previous regime of wave action. So right now, maybe the waves are smaller or the tides are lower, and so it's really the wave action only is reaching to here, and so you got a berm building up here. The sand builds up there. Everything below it is being, influenced by waves at some point during the day. However, maybe a month ago or 2 weeks ago, there was bigger waves and the tide was higher, and in which case this was the berm. And so all this sand that's right here was actually not there. So this kind of mass of sand has just built up in the last few weeks. And so then this is oftentimes referred to as the storm berm. It's a berm that formed during a higher energy wave regime. Okay. So you rarely get a little cross section of the sand, but this is an example of one where you can see unconformities in here. So here's some sand layering where this was basically the back shore. It's more or less flat, and then you must have had an increase in wave action and maybe possibly higher tide, and so now you see it's sloped. So you got this unconformity here. So what happened is this was the back shore, so the berm was probably out here, and then something changed, a bigger storm or waves came in, and the berm shifted to farther back. And so now you see the slope. This was the beach face. And then now the berm is off to the left of the picture. So we see in this picture evidence in the sediments of the berm and the beach face changing. And so that's a really unique thing about beaches, is they are constantly changing on an almost daily basis, and definitely over the span of a couple weeks. If you go and make measurements and you come back a couple weeks later, things have changed. It's constantly changing, constantly reacting. The sand is always trying to react to whatever the size of the waves are or the high and low tides. So one more picture. This is again from Huntington Beach. You see the cliffs back here now. And so this is bedrock, all right? And underneath the sand here, that bedrock extends. So the black line is showing the contact between bedrock and either the air, a free surface, or bedrock and the sand. So the yellow would be the sand, and the black is the bedrock underneath. Okay, so in a cross section, we consider this, this might be a coastal terrace up here, and then you have a sea cliff. In this case, it's not very steep. And then you have some sort of gently sloping towards the ocean, this unconformity, this erosion surface. And this is called the shoreline platform, also known as the wave cut platform. So this is bedrock that is being eroded into this shape by wave action and sand moving back and forth. And then the sand is piled on top of it. And this will come in a little later in the lecture. You'll see why this is important. But where the cliff meets the shoreline, we call this the shoreline angle. This is important because this is the location of this is dictated by the highest tide that hit this area. So for example, if tides suddenly get higher and the waves get bigger, and sea levels up here, what's going to happen is this part of the cliff is going to erode and it'll extend the shoreline platform inland, a new cliff forms, and now your shoreline angle is right here. Okay, so this is sort of telling us the maximum extent of wave action and high tide over a certain amount of time. Some other kind of side note interesting features of beaches is in various areas you see these what they call beach cusps, these sort of like semicircular shape to the beach. And I'm just kind of pointing these out because they're kind of interesting because nobody truly understands how they form. So this is some satellite view from Google Maps of San Onofre, kind of southern Orange County. And there are nice big landslides here, but what I'm pointing out are these things, these beach cusps, these little semicircle things that seem to form. Down on the beach, they look like this. And, nobody really understands exactly what's creating these things. The best guess is that they form when you have a combination of waves coming from different directions. So you may have waves coming in from the northwest and from the south, and the movement of the waves at the beach is sort of eroding these little embayments, and you're getting these beach cusps forming. But it's still sort of, up in the air as to exactly how these things form over time. Here's another picture of them. And they're a little more permanent here because you notice that these are sizable rocks. They're not just sand. So it takes a lot of energy to destroy these. So these things have persisted for years and years. Whereas in sand, if it was just sand, it would get moved around and destroyed pretty quick. Okay. So I talked a little bit in the last lecture how most of the big wave action in Southern California comes in the winter because we're closer to those big storms in the North Pacific that occur in the winter. So there's two cartoons here I'm going to show you. This is a cartoon of Southern California in the summer. So what it's trying to show is that the summer waves are smaller, and what they're doing is they're pushing sand up onto the beach. So this is your wave cut platform right there. This is your beach cliff, and this point where they intersect is the shoreline angle. So in the summer, small waves are pushing sand up on the beach, and the wave action is not hitting the bedrock cliff. In the winter, you get larger surf, larger waves, and so what that does is that moves the sand out to lower energy environment. It gets deposited out here, and now you're beating on the cliff and causing erosion. So winter is always when we have these erosion problems along the coast. So there's a big difference in California between summer and winter, and you can see these at a lot of beaches in California where you'll go in the summer, there's sand, parts of Palos Verdes, Santa Barbara, Malibu, where there's coastal kind of cliff areas. In the winter, you go back to the same beach and there's no sand at all. It's just literally you're walking on bedrock platform at the coast. Quick example of erosion problems that can result. So this is just 5 or 6 months of time. This is obviously old pictures from 1979, but where they have dropped these big rocks of kind of granitic rock or crystalline, relatively resistant rock along the coast to try to prevent coastal erosion of this street. But what happens is oftentimes the sand erodes out the bottom part, and the waves erode the sand out from underneath, and then these things just roll down. And so that's basically what happened here. A lot of storm activity removed the sand. These big rocks moved and rolled down deeper, and then the waves were pounding right on the coast. And within a few months, it completely destroyed this little coastal section of road that had been built here. Okay. And so now I want to talk a little bit about comparing tectonic environments. So we can categorize coastlines as either emergent or submergent. And so this is relative to the shoreline or sea level. So an emergent coast is one that is rising due to tectonics relative to sea level over time. A submergent coast is sinking relative to sea level. And the important point is that this is relative. So a submergent coast, like the east coast of the US, doesn't necessarily mean the coast is physically sinking. It just means that sea level is rising faster than the coast is coming up. And since there's not active tectonics on the east coast, it's really not moving up or down at all. It's just that sea level is rising. So that coast is getting inundated. It's a submergent coast. So emergent coasts out here in the western US tend to have really high erosion rates relative to sediment supply. And that means that we get very steep topography and cliffs along much of the coastal areas. Okay, so this is a picture of Big Sur. You see these coastal cliffs. In many places in California, we also see coastal terraces. Coastal terraces are sometimes referred to as marine terraces. And that's these flat spots along the coast that have been lifted by tectonics. There's another one back here, probably one right there. And this is basically a wave-cut platform that formed underwater, but then the coast was lifted up by tectonic activity, and now this is elevated above sea level, and so it's preserved. So at some point in this cliff, there'll be a contact between beach sands on top and bedrock underneath. So this whole thing has been lifted up. So these are wave-cut platforms that are preserved during sea level high stands, and then they get uplifted. Here's an example of one of those shoreline angles at a modern shoreline angle. This is in Santa Barbara. So here's your vertical cliff, and you notice that on the beach there's a lot of bedrock exposed. There is some sand, but there's bedrock sticking up. You can see that the trees that were previously on this cliff are falling over as the cliff erodes. So over time, this cliff is eroding backwards as sea level slowly rises and kind of eats into the cliff. So this shoreline angle is also migrating this way over time. And so if there is a period of tectonics activity that lifts this coast up, this shoreline angle will be preserved and lifted up into the topography. Okay? Or if sea level goes back out, this is not changed, right? Sea level will just go out and it'll reoccupy its same platform. So that's why these preserved shoreline angles uplifted on the marine terraces are generally a sign of a sea level high stand that was then lifted up. Another example along the California coast. So here you can see the wave cut platform sticking up. It's not perfectly flat because the rocks erode a little bit differently. There's more cemented sections and less well cemented sections. But in general, these are, on a rough scale, relatively flat and gently sloping out towards the ocean. So coastal erosion, we're not going to talk a whole lot about it. I just want to mention a couple things. A couple different ways it can happen. One, you can just have direct contact of the waves hitting the base of the cliff. And we saw evidence of that on the very first day of class. That kind of maintains the steep cliff. Here's an example in Santa Barbara area where they built this fence to try to protect the cliff, but you can see that it's still experiencing erosion way up here. So I show this because the waves are not actually making it up here, but there is spray from the ocean. There's just kind of the ocean fog that's salty. So this is just weathering over time just from indirect exposure to the ocean and the ocean air. So it doesn't necessarily need to be direct wave action. You can also have erosion in some places by dissolution of the rocks just from the fog and coastal spray coming up from the waves. Okay. Again, more examples from early in the class where we talked about the fact that this cliff here tells you that at some point in time the waves will actually reach that point to maintain that steep cliff. And so this is a couple pictures from UCSB, the beach right below the university, showing how this waves can come in over time and reach the bottom of the cliff. And anytime this is generally happening during big storms and high tides, and when that occurs, even on the news down here, you hear these big, scramble to try to save some of our coastal communities. The newscasters are always going to Seal Beach, where people are piling up sand to try to protect the houses built along the coast. So they'll take big tractors out there and try to dredge, pick up sand off the beach and pile it up to try to make a buffer from those waves. So here's an example from Surfside, kind of the north end of Sunset Beach in Huntington area, where this tractor is moving sand and try to create a barrier to prevent that coastal erosion from happening. So I'm going to diverge a little bit. We've talked about uplifted tectonic coasts. Another type of coast that's very different than what we have in the U.S. is what's called a carbonate coast. This is going to happen in more tropical waters where you're creating coral reefs. So a carbonate coast, the processes are very different because the reefs are really controlling the coastal morphology. A lot of these islands in the South Pacific are rimmed by reefs, so the waves don't really actually hit the beach most of the time. Instead, they break on the reefs and their energy gets dissipated. But these pictures I show because this is reef that was lifted up after the 2004 earthquake in off the northern island of Sumatra in Indonesia, where a big subduction zone, it's very fast-moving tectonics here, lifted this reef in one single earthquake, and that's why it's all white. It's basically died off now because it's above sea level. But the location of the shoreline actually moved drastically out, and all this reef was brought up and exposed. Okay. Going back towards the east coast of the U.S., where we have a submergent coast, this is again where sea level is rising relative to the land. So this is the coast of Georgia, and you see it looks very different than California. It's just full of these inlets. So these are old kind of river stream valleys that are being inundated as the water level rises, as sea level rises. So you have all these little barrier islands and islands that are separated from the coast. So, no coastal cliffs. You have kind of sand dunes from lots of sand present and wind blowing the sand up onto the land. These places have, like I said, these barrier islands and full of dunes. Behind that will be a lagoon and some tidal mud flats and then marshy areas. And so there's a whole lot of coastal erosion science that occurs on the east coast of the U.S. because they're extremely vulnerable to hurricanes and storm surges as those hurricanes come in. And a lot of these lagoons then will have a certain outlet through one of these barrier islands. And these things, they've built on these, but these are ephemeral features. They're constantly changing. The sand is moving up and down. These inlets sort of form in big storms, and then they'll seal up with sand as it gets brought up or down the coast. The next big storm will bust a whole new inlet somewhere else. So they're constantly changing. And the fact that people have now built on these barrier islands means that there's a lot of engineering that needs to go on to try to preserve those houses. Otherwise, they'll get destroyed, but they're trying to preserve them as long as they can as sea level comes up. So here's an example of one of these. So you see this inlet. This is a little barrier island, and at the mouth of this, you form these little deltas. You kind of have a delta from where that forms when the tide's going out, and inland you get a little delta that forms from the incoming tide. Okay, so when the tide's going in, it's depositing sand here. When the tide's coming out, it's depositing sand here. And so we see these features in a few places along the California coast. The south end of Bolsa Chica is one, where they've made an artificial inlet to try to allow water to come into the Bolsa Chica wetlands. And you get these little deltas forming on the inboard and outboard side of those. Okay. So I want to finish up this lecture talking a little bit more about coastal terraces. As we mentioned, the kind of key characteristics is that terraces are an uplifted wave-cut platform. Then at the ocean side of the terrace, there'll often be a cliff, right? And then that leads down to the modern wave-cut platform just below modern sea level. At the back end of the terrace, oftentimes there are preserved sea cliffs from when this was the wave-cut platform. Now, those, if they're old enough, they're not very well preserved. You get erosion coming down and covering them, and they can be hard to see. So here you kind of see a degraded, this would have been the old shoreline angle right there, but it's probably buried under here. You need an outcrop in a canyon or something to see it. But the shoreline angle, again, is important because it's a marker for paleo sea level, right? Because we know that sea level is at its maximum today at that shoreline angle. So if I wanted to measure how much uplift there's been in this part of the coast using this marine terrace, I would not compare the elevation right there to modern sea level. I would want to compare the elevation at the shoreline angle, which is going to be higher, because this is sloping downward, and sea level would have been reaching all the way up here. Okay, so I'll show you another example here. But these terraces are important because they are recorders of coast seismic deformation, of uplift of the coast. So generally, California, we're using terraces. In other parts of the world where you do have coral reefs, you can use reefs as markers, like in that picture I showed a few slides back from the 2004 earthquake. But you've got to be able to differentiate between tectonic uplift and just sea level change. So tectonics is sort of slowly lifting the coast, but at the same time, sea level is coming up and down through time, right? Through glacial periods, it's coming up and down. So you need to know how high sea level was at the time that the terrace formed that you're using as a marker. So if I find a couple of terraces in an area, and this is a cross-section view, so here's the lowest one, here's the next highest one, here's the next highest one, and so on. So if I say I get this terrace, and I want to know how much it has been lifted above sea level, if I just compare the elevation of that to modern sea level, I will not get the correct answer, because at the time that this terrace formed, sea level was not where it is today. It was actually higher. So this blue line is showing a sea level curve through time. So this is 100,000 years ago, 50,000 years ago, today. So what you would do is you would date something. You'd get a date on this terrace, and you say, oh, okay, this terrace is 120,000 years old. and it's currently 155 meters above sea level, but at 120,000 years ago, sea level was 5 meters higher than it is today. Therefore, I would not use 155 meters above sea level as the uplift of this terrace. I would instead use 150. I have to subtract the difference of what sea level was at that time. Okay, so I know this is a little bit difficult maybe to get from the lecture. Normally we're meeting in class and we're kind of doing some exercises with this. But think about this a little bit, because this is kind of a really interesting feature and advantage of these marine terraces, is they can allow us to document how fast the land is rising. And again, only the sea level high stands are preserved, because if the sea level goes down, it doesn't really change the coastal morphology at all. It just goes back out. And if it comes up higher, it destroys the cliff, right? So really, the old paleo cliffs that are preserved are the high stands of sea level that are being preserved as they get lifted up by tectonics. And since sea level has fluctuated over Pleistocene and throughout all of Earth's history, we don't have this constant marker. We need to compare the age of the terrace to see what sea level was at the time that it formed. Okay, so I'm going to go through this kind of quick. This is sort of reiterating what I said in a previous slide, but if you want to calculate the tectonic uplift of an area, and this is an example from Santa Barbara, the first thing you do, you make a map of the marine terraces, and these little shaded gray areas are terraces along the Santa Barbara coast. And then you need to date that terrace to find out the age of it. Then you take that date and you use it to check what the sea level curve was to find sea level at that time that that terrace formed. Then you can calculate the amount of uplift and the rate at which the coast is rising. Okay, so an example from Santa Barbara, there's been a couple terraces mapped near Santa Barbara City College. This is another kind of cross-section diagram like I showed before, where this is the elevation of the terraces on land. And so somebody's marked off, these terrace elevations that they've mapped. And this is the sea level curve over the last 140,000 years. So they figure out the age of the terrace, compare that to what sea level was at that time, and throughout most of the last 100,000 years, sea level was lower than today. So the uplift is actually greater than what you see in the landscape today. And then you can get a rate and an amount of uplift. Okay. Just finishing here with the lab from a few weeks ago. These terraces along the coast that we said are actually probably fluvial in origin, but as you get down towards Newport, you've got definitely marine terraces that are forming as the San Joaquin Hills are coming up. This is a good example of where this work could be done, where you can date these terraces and get an idea of how fast uplift is occurring along the Newport-Inglewood Fault. Okay. And one last slide, Palos Verdes. We looked at the landslides on Palos Verdes, but this map is showing in yellow all the marine terraces that are present on Palos Verdes. There's a whole flight of them. They've mapped 12 or 13 levels of marine terraces as Palos Verdes has just slowly lifted up through time, and sea level is just cutting notches in those terraces as it comes up. Okay, you can kind of see these flat terraces on Palos Verdes preserved in the landscape. Okay, so I'm going to quit lecture there, and we'll see you guys on Friday.